Now, all through our conversation in ignition system, we referred to fuel lean out. Fuel lean out is caused because there's an error or an imbalance in the fuel control or fuel delivery system. We define fuel delivery as the mechanical side of the system, the fuel pumps, the fuel lines, the fuel filter. And then the PCM is going to be doing the injector pulse width control. How long is the injector open? And if the pressure applied to the injector is correct and the injector is clean, we'll get the right amount of fuel in. And we've got to have a good manifold sealing. Now, that's something we throw in, not that it's important, but we can't have imbalanced air entering the engine. The fuel control side is we try to make a correct fuel calculation for the proper air-fuel ratio for operating conditions. Now, we're going to have to utilize the PCM inputs for this. They're going to be measuring the inputs and seeing what's going on. But while we're doing this, we're also going to be monitoring what's happening. On OBD2, we have a fuel monitor. It's in the software, so a continuous monitor that runs in the software whenever the engine's running. It's entirely software basis, and it monitors the fuel system trims. Now, we're going to talk a lot about fuel system trims. But let's get down to talking about why we're going to need a trim. We take our fuel control where the PCM determines how much air is entering the engine. Then we base our calculation on a number of factors, and we're going to talk about all of them. And we're going to see how much fuel is required. And then we're going to turn around and we're going to command an injector pulse width. Now, the amount of fuel that's actually delivered is dependent upon the ability of the mechanical side to deliver fuel. If the pressure's wrong or if the injector's dirty, it'll be wrong. If fuel control isn't right, it's going to be wrong. And we'll have fuel trims for that. But let's talk about how we make these calculations. The calculations are critical. Our load calculations are using two different methods, and they'll cover almost all the vehicles entering your service bay. That's the MAP sensor and the mass airflow or MAF sensor. Let's start with speed density system that calculates the air entering the engine by using the MAP sensor values. Calculations it's going to use are engine load, engine speed, air density, ambient air pressure, baro, engine temperature, and finally, engine size of volumetric efficiency. Now we're going to talk about each one of these. Let's break them down one at a time. Engine RPM is quite simple. It's determined by the crankshaft position sensor. And we know how important that is and exactly what it's going to do for the injection. Now, the engine load is measured by the manifold absolute pressure sensor. It determines how much fuel should be added. The air temperature is measured by the inlet air temperature to check the density of the air. The inlet air temperature is a correction that we sometimes overlook. It varies the quantity, the pulse width, since air affects air density. Hot air takes less fuel than cold air. Colder air is more dense. 70 degrees is generally considered zero correction. Higher temperatures will use less fuel to compensate for lower air density, except that very high temperatures, we can go rich for cooling effect on the engine in overheat conditions. Lower temperatures tend to be richer because the volume of the air, the density has gone up. Now, a bad reading will affect the PCM's attempt to keep the air and fuel in the proper ratio proportion. And this also affects the regulated pressure on some of the newer systems that have returnless systems. Engine operating temperature is measured by the engine coolant temperature. We've got to have our electronic choke, for lack of a better thing. The true term is electronic enrichment. Electronic enrichment is going to keep us enrichment till we get somewhere between 150 and 160 degrees Fahrenheit. And finally, every engine has a specific volumetric efficiency factor, and it's programmed right into the PCM. So our MAP is measuring 18 inches of manifold vacuum in this particular case. And we've got our signals over here for the crankshaft position sensor, and we've seen how they work. We've got our inlet air temperature says it's 75 degrees, meaning we need very little correction. And we have B+ applied to our injector. Then we're going to ground it for our injector pulse width. This is our basic pulse width. If there's something wrong with this, we'll have to adjust it. Now let's take all that nice theory and talk diagnostically for a moment. If you have a major fueling problem with the incorrect fuel pulse width, injector pulse width, your first step is to look at the map. Does the map look right? That's our main load sensor. Is it indicating the correct information? Do we have a good clean crankshaft position sensor? Inlet air temperature, does it look right? You need to answer the question, why is fuel control wrong? Now let's stop and think about this. We have a dividing line. I'm going to talk about it here. This is very important. If we are too rich, the computer should be asking for less fuel. If the computer is asking for more fuel when we are too rich, it is wrong. Some input sensor is doing the wrong thing. If we have too much fuel and the computer is asking for less fuel, it's taking the right action. Go to fuel delivery system. Let me say that again. We're going to try to divide fuel delivery from fuel control. We can determine if fuel control is wrong because we will be too rich or too lean, and the computer will be commanding the same symptom we have. If we're rich, it's commanding rich. This is what you're looking at. Do not go beating up on the fuel delivery system until first you correct fuel control. For instance, I'm running very rich. Fuel trim says it's leaning it out. The computer's doing the right thing. We said before, it's going to modify it. It's going to change the basic pulse width. And it's going to, after all these adjustments are made, and any one of them can cause it to be wrong, we have to look at fuel trim, long-term, short-term. The mass airflow method makes our life much simpler. It measures the air entering the engine. The sensors mounted out in the intake path make sure you don't have any leakage after it's the mounting. It's going to actually measure the mass or the weight of the air. Then the PCM matches that volume of fuel, the incoming air, with the correct fuel mixture. We went through it before. It's pretty simple. We've got a crankshaft position sensor. We've got a mass airflow. They're going to give us our base pulse width, and then we're going to modify it with TPS, coolant, park neutral, AC, short-term fuel trim, long-term fuel trim, and things like other accessories. For instance, if we happen to have fuel composition sensor on a flex fuel, it's part of the deal. But let's diagnose. For the PCM to command the correct injector pulse width, it must have the correct input information. To begin the diagnostic, stop and decide what direction does the data send you. Do you have a rich condition? Do you have a lean condition? Know where you're going. Then try to decide, depending on the system, which one of these could be causing your problem. What could be the observed problem? Which sensor must be working normally for the PCM to make the correct air fuel calculation, and which one would give you the condition you're looking at to make the calculation so wrong. Now, scan data, don't ever sell it short. This is time to decide what all the scan data is pointing to. Make sure you understand that there's no DTCs. If you have mode 6 and understand it, go look at it. It can identify some things that'll help you. We'll talk about more of that later. History DTCs, pending codes, one that's fixing to mature but hasn't matured yet. And if you've got freeze frame data, use it. Freeze frame data for fuel monitor is really viable. Tells you where you had the problem. And the vehicle performance clues. Is it surging? Is it seem to have low power at high end? Rough idle? What all is going on? Now, when testing fuel control delivery, you need to understand the monitor. It's going to be used short-term fuel trim. The PCM acts quickly here to correct for fuel mixture. Long-term fuel trim, which comes in after the vehicle's out of cold and rich between 150 and 160 degrees. The PCM will make small changes in fuel delivery to bring short-term back into the normal range and then store that into memory. And it's a very organized way it stores into memory. We're going to talk about that. So short-term reacted quickly to incorrect mixture. We're going to talk about that when we look at the oxygen. Let's talk about short-term and long-term. We've got 3 of them. They refer to the adjustments being made dynamic while the vehicle is being driven to the base fuel delivery table so we get the right air-fuel ratio under a wide range of conditions. And there's 3 of them. There's short-term fuel trim, which is a parameter ID. There's long-term fuel trim, which is a parameter ID We see both of those in all scan data. Some of them shows total fuel trim, which is the combined total, which is what's driving the service code. The check engine light will be driven off the total fuel trim. Let's start defining these a little better. Short-term fuel trim refers to the quick adjustments being made in response to the oxygen sensor reading. Stop and let that sink in. It's responding to the oxygen sensor reading. We'll show you how it happens later. Now, the long term, as we said before, is used to compensate for issues that are present over a longer period of time. It responds slowly to short-term fuel trim being out of the normal range. Fuel trims are all expressed percentage. Positive values indicate a lean condition. We need to add fuel, positive. Negative values indicate a rich conditions. We need to subtract fuel, a minus. You need to a starting point here. Anytime you're doing a diagnosis and you think you have a fuel control problem, look at long-term fuel trim. It tells you where things are. It is the information about what the PCM has already done and learned and stored in memory to correct operating conditions. Short-term responded to the oxygen sensors, staying either rich or lean too long for normal operation. If we go rich, that's normal. As long as we go lean, shortly thereafter. But if we go rich and stay there, short-term fuel trim is going to start leaning out. If we go lean and stay there, short-term fuel trim is going to go positive and start adding. What's going to happen after it's out of range? The long-term fuel trim will make adjustment to bring the short-term and the oxygen sensors back to normal operation. They will look normal, but the difference will be stored in long-term. Good fuel control depends on good oxygen sensor. Good fuel trim depends on good oxygen sensor. They're an important part of this. Good oxygen sensor activity depends on good fuel control. The oxygen sensors can look stuck full rich if we have a full rich mixture. Now, it's impossible to talk about long-term and short-term fuel trim and oxygen sensors at the same time. So let's talk about fuel trim first, then go look at the oxygen sensors. Now, the oxygen sensor drives the short term, which then drives the long term. I know this is the third time we've said it, but I really need to say it another half a dozen. Long term is driven by short term. Short term is driven by the oxygen sensor. How do we decide that? Well, the oxygen sensor signal causes changes in short-term fuel trim values, which then cause changes in the long term. Was the mixture wrong, or was the oxygen sensor reading wrong? We're going to talk about that when we get to oxygen sensors. But here's what's looking normal. They're both rocking along. This middle is zero. They're both perfectly balanced. They're reading zero. There's no changes. The car's running fine. Here is an engine recovering from an overly rich fuel mixture. We did an injector cleaning where it was far too rich. Now, you're going to watch live. Short term in red. It's going to react quickly. The long term, which is at minus 10%, it's been taking fuel away, is only going to react after short term has been wrong for a number of seconds. This entire test drive, or recovery period really, is only 100 seconds long. Watch what happens. We see short term take off. Long term is just now moving. It's trying to bring short term back down. It's pulling short term down and coming up, and what's eventually going to happen is it's going to bring short term back to the 0 point in the center of the chart. Here we are. It's been reacting to this change. So we've now looked at about 75 seconds. We've gone from minus 10% long term to right around 0%. It's been a little above, a little below, right on zero for the last few seconds. But look what happened. Short term took off right away, started making changes. The blue one, long term, took 10 seconds for it to react to the changes that were being made in short term. Then it started going up. But notice once short term starts kind of leveling out, when long term starts coming up, it's bringing it back into range. So here's what we said. The red one responded to changes in the oxygen sensor. That's short term. The blue, long term, did not react until the short term had been wrong for a period of time, and then it made corrections to bring them both back to 0% ideally. To really say what happened here is We just got through fogging the intake and cleaning the injectors on a car that had excessively high long-term fuel trim. When we're looking back at this zero we're at now, it's telling us we have fixed our dirty fuel injectors, corrected our long-term fuel trim. We like to see long-term below 5%, but really get upset when it gets anywhere at around 10%. Now, long-term fuel trim, load factors. Long-term is not just a reading. It's a matrix, a group of cells arranged by engine RPM and load. Each one of these cells has a specific long-term number in the register. The register is a place in memory. Now, this is a little bit confusing to some people, but as we go through it, you'll see it. We have a scan tool that does a good job. Let's look at what's happening here. Look at the left. We have throttle position going up, 0 to 90%. Across the bottom, we have engine RPM. Each block is a representation. Now, in this particular software on the eScan, it maps out these blocks for us and records the long-term fuel trim in each block. Setting at idle, we have 2%. Getting up at 100% throttle, 1500 RPM, we've got plus 5%. Nothing particularly bad. Let's go look at a problem and see what we're going to look at. So our long-term values are going to be read in these boxes. That's the cells we went through on this particular test drive. Now look at this test drive. Over here at 55% throttle with RPM at 2500. At the higher loads, we start getting into problems. If we go higher in RPM or higher in throttle position, the numbers turn red. We are not getting enough fuel. Could this be an indication of low fuel volume from the fuel pump? Entirely possible. We're going to talk about testing to identify this. When we have high demand, this vehicle is not able to meet the demands. It's all part of the diagnostics. So long-term is a bigger issue. But if the mixture is not corrected by both short-term and long-term combined at their extreme values, a fuel trim diagnostic trouble code will be set. When the PCM determines that the fuel trim is out of operating range, one of the following DTCs will set. P0, 171, bank 1, 2 lean, 172, bank 2, 2 rich. P0, 174, bank 1, 2 lean. P0, 175, bank 2, 2 rich. If we have problems here, we need to make corrections to fuel delivery before we try to fix anything. But let's go back and look at what's going on here. Here's our normal values. They're looking good. They're working normally. They're not making huge corrections. We don't have a fuel delivery problem. If they're way out of range, if they're plus or minus 5%, we like to find out why. Older vehicles, high mileage, sometimes we live with 5%, but we like to see them under 5, never anywhere near 10. So we're looking at things like here, short-term, B1, minus 1%, long-term, B1, 3.1%, short-term, B2, 0%, long-term, bank 2, 3.9. That's typical type readings. We haven't got anything to worry about here yet. But study, are you running rich or are you running lean? Both lean and rich mixtures can cause misfires. And we are talking about misfire and fuel control together because of this very reason. If the engine is running too lean or too rich, diagnose the fuel system for control and delivery. And remember, the EGR can cause engine operation to operate in the incorrect air-fuel ratio if it's open at the wrong time, if it's not following commands. What I'm trying to say, if it's leaking, it can cause improper operation. Oxygen sensors and fuel sensors are used to signal rich and lean conditions to the PCM. You've got to verify proper operation before going too much further. Since fuel trim is so dependent on the oxygen sensor, we're going to go a detailed analysis of oxygen sensors and wideband fuel control for this class so you have a good understanding of how they're working. If they're lying to us, again, fuel trim is wrong.